everyone. I welcome you all to this digital classroom for the subject control systems. In the previous lecture, we solved few example problems related to the construction of root locus. In continuity with that, let us solve few more example problems related to the construction of root locus. You can take down this question. A feedback control system has an open loop transfer function g of s into h of s, which is equal to k divided by s into s plus 3 into s square plus 2s plus 2. Draw the root locus as k varies from 0 to infinity. And also find the value of k for theta equal to 0.5. Given the open loop transfer function, and we have to construct the root locus by following the rules. Once after constructing the root locus, we have to find the value of k for zeta equal to 0.5, where zeta is nothing but the damping ratio. First, let us construct the root locus. Then, let us calculate the value of k for a given damping ratio. Root locus is always symmetrical about real axis. The first step in the construction of root locus is to get the general information about the number of open loop poles and zeros as well as the number of branches from the given g of s. With respect to the given g of s into h of s, we have 4 poles at s is equal to 0 and at s is equal to minus 3, as well as solving this equation s square plus 2s plus 2. As the highest power is 2 here, we get 2 roots at minus 1 minus j as well as at minus 1 plus j. Therefore, we have a total of 4 poles, hence p equal to 4. We don't have any zeros in this case, therefore z, the number of zeros, will be equal to 0 in this case. And we know that with respect to rule 1, p greater than z, therefore the number of branches, root locus branches, will be equal to p, which is equal to 4 in this case. Hence, we have 4 root loci in this example. As p greater than z, the number of root loci will be equal to number of poles, that is 4 here, and we know that when k is equal to 0, the root locus starts with an open loop pole and it terminates at an open loop 0 when k reaches infinity. Therefore, p poles will be terminating to z zeros. In this example, as z is equal to 0 here, the number of zeros is nil here, none of the pole is going to terminate at a 0. Hence, the rest of the p minus z poles will be terminating to infinity. We have number of poles as 4 and the number of 0 as 0. Therefore, all the branches which is emerging from the 4 poles will be terminating to infinity. That is why it has been written here p minus z is equal to 4 branches which is going to terminate at infinity. Therefore, the starting point will be at an open loop pole at s is equal to 0, s is equal to minus 3 as well as at s is equal to minus 1 plus or minus j when k equal to 0. And the terminating point will be at s is equal to infinity, comma, infinity, comma, infinity, comma, infinity. As we don't have any 0 to terminate with, all the 4 branches will be terminating to infinity. Step number 2. Step number 2, with respect to step number 2, we have to draw the pole 0 plot and we have to identify the section of real axis for the existence of root locus. As well as we have to predict the minimum number of breakaway point or a break-in point using general prediction. Let us plot the poles and zeros. We have a pole at s is equal to 0 and at s is equal to minus 3, and we have a complex conjugate pair at minus 1 plus j, that is the intersection point of the real and imaginary. We have a complex conjugate pole here and another complex conjugate pole in this intersection point, minus 1 minus j. Now we have to identify the region of root locus. We have two poles on the real axis, one at s is equal to 0 and the other pole at s is equal to minus 3. Let us take any point here on the positive region of the real axis. And if you look into the right side, we have to ask the question that whether you could be able to see any odd number of poles and zeros towards your right. It's no in this case. Therefore, root locus does not exist in this region. I can write it as NRL. Now let me take some point here in the negative real axis and let us look into the right side. Now you could able to see one pole at s is equal to 0, which is an odd number pole. Therefore, root locus exists towards the left of a odd number of poles and zeros. Hence, you can highlight this region. Root locus exists towards the left of an odd number of poles until it reaches the pole at s is equal to minus 3. Now, if we take a point somewhere here and if you look into the right side, we have the count of the poles and zeros here in this case as 1 at minus 3 and the other at 0. So it is even number now in this case. Therefore, root locus does not exist in this region. I can write it as NRL. Hence, it is very clear that the region of root locus exists between 0 and minus 3. Let us predict for the breakaway point. We know the procedure to predict for the breakaway point. If we have any two adjacently placed poles, yes, we have two adjacently placed poles. And if it is in the region of root locus, yes, it is in the region of root locus. Hence, there exists minimum one breakaway point. Okay, so breakaway point exists between 0 and minus 3 using the prediction. And in the coming steps, let us see that at which point it is located exactly. Here is a clear plot of the poles at 0, minus 3 and at minus 1, minus j as well as at minus 1 plus j. And we know that it is an intersection point of the real and the imaginary at which we get a complex conjugate pair. And the starting point is at s is equal to 0, minus 3 and minus 1 plus or minus j. And the root locus exists between 0 and minus 3. This gives the region of the root locus and you can represent it as RL. Moving on to step 3. Step 3 and 4 comes hand in hand and we are going to calculate for the angle of asymptotes as 4 branches are approaching to infinity. Hence, 4 asymptotes are required. That is, we will be always having p minus z number of asymptotes. As p is equal to 4 and z is equal to 0 here, 4 asymptotes are required to guide all the branches which is emerging from 4 poles to reach infinity. The asymptotes are the one which is going to guide these branches which is emerging from the pole starting from k is equal to 0 towards infinity. The formula to calculate the asymptote is given by theta equal to 2q plus 1 into 180 degree divided by p minus z, where q ranges from p minus z minus 1. 4 minus 0 minus 1 that is 3. Therefore, Q ranges from 0, 1, 2 to 3. When Q equal to 0, theta will be equal to 180 degree divided by 4 minus 0. That is 180 degree divided by 4. Hence, theta 1 is equal to 45 degree. When Q equals to 1, 2 plus 1 into 180 degree, that is 3 times of 180 degree divided by 4, we get theta 2 as 135 degree. Substituting for Q equal to 2, 2 into 2, 4 plus 1 into 180 degree divided by 4. Hence, theta 3 is equal to 225 degree. Finally, substituting for Q equal to 3, 3 into 2, 6 plus 1, 7 times of 180 degree divided by 4. Theta 4 will be equal to 315 degree. So we have obtained 4 asymptotes. Step number 4 is to calculate the centroid. Determine the centroid, and we have to sketch a separate plot with respect to step 3 and 4. The formula to calculate the centroid, sigma, is given by summation real part of poles minus summation real part of zeros divided by p minus z. We have the real part of pole as s is equal to 0 and at s is equal to minus 3. Then we have a complex conjugate pair at minus 1 plus j as well as at minus 1 minus j. We have to consider only the real part. Therefore, the real part in this complex conjugate pair is minus 1 and here it is minus 1. Hence, I can write it as minus 1 and sum up all the real part of poles. Minus of real part of 0, we don't have any 0 in this example, therefore it is 0. Divided by p minus z, p is equal to 4 and z is equal to 0. So we have written the denominator as 4. Therefore, centroid will be equal to minus 1.25. Now, with the centroid as a center of the asymptotes, exactly at minus 1.25, we have to draw the angle of asymptotes at 45 degree, 135 degree, 225 degree, as well as 315 degree. Let us plot the asymptotes at these angles 45, 135, 225 and 315 with sigma equal to minus 1.25 as the center. Mark the location of all poles and zeros. And then we can exactly mark the location of the centroid, which is at minus 1.25. Now with centroid as center, we have to make use of the protractor and mark the angle at 45 degree. Let me take this protractor and with centroid as the center of the asymptote, with centroid at minus 1.25 as the center of the protractor, I've placed the center of the protractor exactly at the centroid, which is marked at minus 1.25. This is your reference. Now we have to mark 45 degree first, the first angle of asymptote, exactly 45 degree. This is exactly 45 degree. Let us represent the angle of asymptotes. Then the second angle of asymptote is at 135 degree. Let us mark for 135 degree. This is exactly 135 degree. Let us mark for the second angle of asymptotes exactly at 135 degree. Let me invert the protractor and let us mark for 225 degree. This angle is 180 degree. This angle will be 270 degree. So 180, 190, 200, 210, 220, and 225 degree. This is exactly 225 degree. And this angle is the third angle of asymptote, exactly 225 degree. With centroid as the center, we are plotting the angle of the third asymptote. Finally, let us mark the fourth angle of asymptote at 315 degree. This angle is exactly 270 degree and this is 360 degree. So 315 is in between this 270 and 360. So this is 270, 280, 290, 300, 310 and 5 more unit. This is 315 degree exactly. Let us have the centroid as the center of the asymptotes and let us mark the fourth angle of asymptote, which is at an angle exactly at 315 degree. Therefore, we have obtained the angle of asymptotes exactly at 45 degree, 135 degree, 225 degree as well as 315 degree with the center of the asymptote at minus 1.25. Let us move on to step number 5. Step number 5 is subjected to the calculation of the breakaway point. We know the procedure to calculate the breakaway point. The first step is to write the characteristic equation 1 plus g of s into h of s equal to 0. The root locus must have a breakaway point which can be found by the following steps. Let us write the characteristic equation 1 plus g of s into h of s. Here given g of s is k divided by s into s plus 3 into s square plus 2s plus 2 and we have to equate it to 0. Further simplification, we get the characteristic equation as s to the power 4 plus 5s cube plus 8 square plus 6s plus k equal to 0. Once after writing the characteristic equation, the next step is to represent k in terms of the polynomial. Therefore, k will be equal to taking all the s terms towards the right side. K will be equal to minus s power 4 minus 5s cube minus 8 square minus 6s. Now we have to differentiate k with respect to s and we have to equate it to 0 and we have to look into the highest power of s. Based upon the highest power of s, we get the roots of that particular equation and we have to check for validity of the breakaway point. Here differentiation of minus s to the power 4 is minus 4s cube and differentiation of minus 5s cube is minus 15s square and the differentiation of minus 8 square is 16s and the differentiation of minus 6s is minus 6. Therefore, after differentiation, we have obtained minus 4s cube minus 15s square minus 16s minus 6 equal to 0. I can write this as 4s cube plus 15s square plus 16s plus 6 equal to 0. As the highest power of s is 3 here, we will be getting 3 roots. Solving, we get s is equal to minus 2.288 and s is equal to minus 0.731 plus j 0.349 as well as s is equal to minus 0.731 minus j 0.349. If you check for angle condition for this complex conjugate pair, angle and the magnitude condition, This complex conjugate pair does not lie in the region of root locus. Hence, it is invalid. Now we have to check for the validity for S is equal to minus 2.288. Let us look into the plots of the S-plane. We have marked with the poles and zeros the centroid, the angle of asymptotes, as well as the region of root locus. Let us mark for the breakaway point exactly at minus 2.288. As this breakaway point lies in the region of root locus, yes, it lies in the region of root locus. Therefore, it is a valid breakaway point. S is equal to minus 2.288 is on the root locus. Therefore, it is a valid breakaway point. Whereas S is equal to minus 0.731 plus J into 0.349 as well as minus 0.731 minus J into 0.349 is not on the root locus. It is not valid. Let us move on to the next step. Step number 6 is to calculate the intersection of the root locus with the imaginary axis. In the previous step, we have calculated the location of the breakaway point at minus 2.288, which is a valid breakaway point. Therefore, it is very clear that the root locus branches will be breaking away and it tries to move from the real axis into the complex plane guided by the asymptote at an angle of 135 degree as well as at 225 degree, and it tries to reach infinity. Of the 4 branches, 2 of the branches will try to reach infinity guided by the angle 135 degree and 225 degree. And the left out 2 branches are from the complex conjugate pole at minus 1 plus j as well as at minus 1 minus j. Therefore, it is very clear that with respect to increase in value of k from 0 to infinity, these branches from the complex conjugate pole will try to emerge at a particular angle, and we call it as angle of departure phi d, and these branches will be guided by the asymptote which is at 45 degree as well as by the other asymptote which is at 315 degree, and it tries to follow the path of the asymptote, and finally at one particular point it tries to intersect on the imaginary axis for a particular value of k, and we can call it as k margin. And if you keep on exceeding the value of k greater than k margin, these branches try to reach the right half of the S-plane, tending to reach infinity, making the system to be as unstable. This is the rough sketch based upon the prediction with respect to the angle of asymptote which is trying to guide all the 4 branches. Having these ideas in mind, let us calculate the intersection of the root locus with the imaginary axis. The first step is to write the characteristic equation. We have found the characteristic equation already, making use of step number 5. The characteristic equation 1 plus g of s into h of s equal to 0 is given by, after simplification we get s power 4 plus 5s cube plus 8s square plus 6s plus k equal to 0. The next step is to generate the route array. Remember, we have to write the characteristic equation starting from highest power towards the least power, finally the constant value, that is a coefficient of s to the power 0. First, let us write the s terms to generate the route array: s power 4, s cube, s square, s power 1 and s to the power 0. Then we know to fill up the first 2 rows of the route array, taking the coefficient of s power 4 as 1 and s cube coefficient of as 5 beside it. Then the coefficient of s square is 8, then the coefficient of s is 6 and the constant k, and the rest of the terms can be made as 0. To fill up the third row first element, we have to make use of the pattern 5 into 8 minus 1 into 6 divided by 5. 8 5s are 40 minus 6 divided by 5, we get 6.8. To fill up the third row second element, we can make use of the pattern 5 into k minus 1 into 0 divided by 5. 5 in the numerator and denominator will get cancelled out, therefore we get k. And the third element will be 0. Moving on to the s to the power 1 row, we have to make use of the previous two rows as the reference and follow the formula 6.8 into 6 minus 5 into k divided by 6.8. Therefore, it will be 40.8 minus k divided by 6.8. And the second element will be equal to 0. And finally, to fill up the last row, that is the s to the power 0 row, we can take the previous two rows as the reference and follow the pattern 40.8 minus k divided by 6.8 into k minus 6.8 into 0 divided by again the same element. This element in the numerator and denominator will get cancelled out. Therefore, we get k here. Once after generating the route array, we know the procedure, that is interpreting with the route array, looking into the first column of the route array. And for stability, there should not be any sign changes. The first element is +1, second element is +5, third element is +6.8, and the fourth element here, 40.8 minus k divided by 6.8. For a system to be stable, this term should be greater than 0. Remember, this should be greater than 0. As well as the last element, k also should be greater than 0. So making use of these two conditions, we can find the range of k. It is very clear that k greater than 0, making use of s to the power 0 row, and we can make use of s to the power 1 row. Therefore, we get 40.8 minus 5k divided by 6.8, we can take it as greater than 0. We have taken equal to 0 here to find k margin. But first, let us find the range of k. So for the simplification, we get k margin will be equal to 40.8 divided by 5, which will be equal to 8.16. Here in this case, k ranges from 0 less than k less than 8.16. If I substitute for k as 8.16 exactly, this first term becomes 0 and the s to the power 1 row becomes a complete 0 row. And this is a special case too with respect to route criterion. If it is a complete 0 row, we used to take the previous row s to the power 2 row as the auxiliary polynomial, and we used to equate it to 0, and the solution of that auxiliary polynomial will give you the roots on the imaginary axis. This we have discussed already with respect to route stability criterion, a special case too. Therefore, exactly at k margin equal to 8.16, this complete s to the power 1 row becomes a complete 0 row. And now we can take the auxiliary polynomial, that is a previous row of the s to the power 1 row, that is a complete 0 row, which is given by a of s is equal to 6.8 square plus k equal to 0. This is exactly when you substitute for k as 8.16. 5 into 8.16 will be equal to 40.8. Hence, the first element becomes 0. In this auxiliary polynomial, let us substitute for k as k margin. Therefore, we get 6.8 into a square plus 8.16, which will be equal to 0. Therefore, simplifying this, we get a square equal to 1.2. Further simplification, we get two roots on the imaginary axis, one at plus j 1.095 and the other at minus j 1.095. And this is the location of the roots on the imaginary axis. And this is the place at which the root locus try to depart and follow the angle of asymptotes and try to intersect on the imaginary axis. Once after calculating the intersection of the root locus on the imaginary axis, now we have to calculate the angle of departure for this complex pole. Let us move on to the next step. The next step is to calculate the angle of departure. As we have a complex conjugate pole, we are supposed to calculate the angle of departure. That is the angle at which the poles try to depart when k ranges from 0 to infinity. The formula to calculate the angle of departure is given by phi d equal to 180 degree minus phi, where phi equal to summation of phi p, that is the angle of contribution by the rest of all the poles towards the point of interest, minus summation of phi z, that is the angle of contribution for the rest of all the zeros. We have marked the location of all the poles in the S-plane. To calculate summation phi p, we have to join all the remaining poles to the complex pole under consideration. Let us consider that we are going to calculate the angle of departure for the complex conjugate pole at minus 1 plus j, and this is our point of interest. Now the procedure is to join all the remaining poles to the complex pole under consideration. So we have rest of all the three poles, one at minus 3, one at 0, and the other at minus 1 minus j. So now let us join all the rest of the poles towards the complex pole under consideration. And now we have to calculate the angle subtended by the phasors joining the pole to pole under consideration. Here now we have to calculate the angle of contribution for the pole at s is equal to 0. Exactly this angle I can represent it as phi p1, and then the angle of contribution of the pole at s is equal to minus 3. This is the angle of contribution for the pole at s is equal to minus 3 towards the complex conjugate pole which is under consideration. And finally, the other pole is the other pair of the complex conjugate pole under consideration. Exactly this angle of contribution towards this complex conjugate pole. So let us calculate these angles. Phi p1. Phi p1 is given by 180 degree. This complete angle is 180 degree minus, I can take this angle to be as x. Therefore, phi p1 is given by 180 degree minus x. X is nothing but this right angle triangle. X is tan inverse of the opposite side is given by opposite side is 1. Therefore, x will be tan inverse of opposite by adjacent, that is 1 by 1. 180 degree minus x gives you phi p1. Now, substituting for tan inverse of 1 as 45 degree, we get 180 degree minus 45 degree, which is nothing but 135 degree for phi p1. Now let us calculate for phi p2, that is the angle of contribution of the other pair, complex conjugate pair, towards the complex pole under consideration. Thus it is seen clearly that this angle will be exactly equal to 90 degree. Therefore, I can write phi p2 as 90 degree. Finally, now we have to calculate for phi p3, that is the angle of contribution for the pole at s is equal to minus 3 towards the complex pole under consideration. To calculate this phi p3 angle, let us take this right angle triangle. So the formula to calculate the angle is tan inverse of opposite side by adjacent side. We have the projection on the imaginary axis, that is opposite side as 1 and the adjacent side 3 minus 1, that is 2. Therefore, 5p3 is 1 divided by 2. That is tan inverse of 1 divided by 2. Therefore, 5p3 will be equal to 26.56 degree. If you sum up 5p1 plus 5p2 plus 5p3, we get the summation of 5p term here. And summation of 5z will be equal to 0 as we don't have any 0 in this example. Let us sum up all the angles. So summation of 5p will be 135 degree plus 90 degree plus 26.56 degree, which will be equal to 251.56 degree. Then summation 5z is equal to 0 degree. And let us substitute for summation 5p and let us calculate for 5. Therefore, 5 will be equal to 251.56 degree minus 0. Now let us substitute 5 in this equation of angle of departure, where 5d is equal to 180 degree minus 251.56 degree. Therefore, after substitution and subtracting with 180 degree, we get minus 71.56 degree. Therefore, the angle of departure for the complex conjugate pole at minus 1 plus j is minus 71.56 degree. As I told you before, as the root locus is symmetric about the real axis, we can write the angle of departure for the other pair at minus 1 minus j as plus 71.56 degree exactly. As I told you before, the angle of contribution for 5p1, 5p3 and 5p2 can be directly calculated making use of a protractor, or you can make use of these formulas. Now let us justify these answers making use of the protractor, and let us justify that 5p1 is equal to 135 degree. Also, let us justify that 5p3 is equal to 26.56 degree making use of the protractor. And let us continue marking the angle of departure for the complex conjugate pole at minus 1 plus j as minus 71.56 degree, as well as for the other pair as plus 71.56 degree. Now let me make use of the protractor and let us justify that 5p1 equal to 135 degree. So we can use the protractor or the formula. We can make use of the formula to calculate 5p1. As we have calculated, the angle is exactly 135 degree. Therefore, if you calculate the angle of contribution for the pole at S is equal to 0, now this angle shows you exactly 135 degree. This is the angle of contribution for the pole at S is equal to 0 towards the complex pole under consideration. Similarly, the angle of contribution for the pole at S is equal to minus 3 towards a complex pole at consideration. Making use of a formula, we have calculated it as 26.56. This angle is exactly 26.8. We are getting around 26.8 towards the contribution of this pole. So both are one and the same, 5p3. So making use of the protractor, we have calculated for 5p1 as 135 degree and 5p3 as 26.8 degree in this case. Remember, you have to maintain proper scaling along x and y axis if you are making use of the protractor. If x axis, the division for one unit is 0.5 on the imaginary axis and the real axis, both should be uniform. The scaling should be uniform, remember. Now let us mark the angle of departure minus 71.56 degree for the complex conjugate pole at minus 1 plus j, that is the angle of departure. So we know that in the S-plane, if you take anti-clockwise direction, then it is positive angle. And if you take the clockwise direction, it gives you the negative angle. Therefore, let me invert the protractor and let us have the center of the protractor exactly at minus 1 plus j, and this is the reference line, and from this reference line 0 degree we have to mark for, from the reference line 0 degree we have to mark for minus 71.56 degree. So we have to take clockwise direction if it is negative degree. So let us take the clockwise direction for marking the negative degree at minus 71.56 degree. So this is 50 degree. You can look into the inner region of the protractor. This is 60 and this is 70, and this will be exactly 71.56 degree. It's exactly 71.56 degree. Now let me mark this angle. And this angle is exactly the angle of departure phi d for the complex conjugate pole at minus 1 plus j. Similarly, for the other complex conjugate pole, which is at minus 1 minus j, the angle of departure is given by plus 71.56 degree. As the angle is positive, we have to take the anticlockwise direction. So let me have the complex conjugate pole at minus 1 minus j as reference. I have placed the center of the protractor exactly here. Now we have to take the anticlockwise direction and we have to mark for plus 71.56 degree. So this is 70 degree and this is exactly 71.2 degree. 71.5 71.5 exactly comes here. Let me mark this. Let us represent this angle. This gives you the angle of departure for the other complex conjugate pair. This is your reference line, 0 degree, and this is the angle of departure, which is plus 71.56 degree. Therefore, making use of the protractor, we have marked with the angle of departure exactly at minus 71.56 degree for the complex conjugate pole at minus 1 plus j, as well as plus 71.56 degree for the complex conjugate pole at minus 1 minus j. This gives you the angle of departure. So we have done with step number 7. Moving on to the next step, we have to plot the complete root locus sketch. Making use of all these steps, starting from locating the poles and zeros in the S-plane, then representing the centroid and the angle of asymptotes, followed by the region of root locus, and plotting the breakaway point exactly at minus 2.288, With respect to the complex conjugate pole at -1 plus j, we have identified the angle of departure exactly at -71.56 degree. Therefore, when k is equal to 0, the location of the complex conjugate pole will be exactly at -1 plus j. And when k increases, there will be a movement of these complex conjugate pole directed by the angle of departure, which is exactly at -71.56 degree. And when k keeps on increasing, it takes a path which will be directed by the asymptotes at 45 degree, and we could able to see the movement here which tries to move, and it will intersect on the imaginary axis. And when k increases, we could able to see the movement of these branches which is guided by the asymptote. And on the other side, for the complex conjugate pole at -1 minus j, the angle of departure is exactly at plus 71.56 degree. Therefore, the branches will be moving towards the other direction, and both the branches will be intersecting on the imaginary axis for a particular value of k equal to 8.16, that we call it as k margin. And when k keep on increases beyond the range of 8.16, these branches tend to move towards the right half of the S-plane, which makes the system to be as unstable. Whereas on the other side, as we have a breakaway point exactly at -2.288, with respect to increase in k, these branches try to move from real axis towards the complex plane, and these two branches will be following the path of the asymptote at 135 degree, as well as for the other branch it will be following the path of the asymptote exactly at 225 degree, and it tries to reach infinity. And this shows the complete sketch of the root locus. And the final step is step number 9. For 0 less than k less than 8.16, the system is absolutely stable. And when k equal to 8.16, the system becomes marginally stable. And when k greater than 8.16, the system becomes unstable. This gives a complete sketch of the root locus. Now let us compare the output which we have obtained with the output which we have obtained from the MATLAB, which has been shown in the right side. In this example, we have a total of 4 branches. And if you look into the complex conjugate pole, we could able to see that the complex conjugate pole is departing at an angle of -71.56, and it is intersecting on the imaginary axis, and one of the branches trying to reach infinity based upon the angle of the asymptote which is guiding it at an angle of 45 degree. And on the other side, the other complex conjugate pole is taking an angle of plus 71.56 degree, intersect on the imaginary axis, and it tries to reach infinity, which is following the asymptote at an angle of 315 degree. And the rest of the two poles on the real axis, which is at s is equal to 0 and s is equal to -3. When k increases, we could able to see the movement of this pole, which is moving in this direction along the region of the root locus, and it reaches one particular point, we call it as breakaway point, and it breaks away and it tries to reach infinity, which is following the angle of the asymptote at 225 degree. Similarly, the other pole, which is at -3, when k increases, it intersect at one single point, that is the breakaway point, and then It tries to break away, moving from real axis into the complex plane, and it tries to reach infinity following the direction of the asymptote at 135 degrees. Therefore, we could able to see the movement of these branches as shown here. The branch B1 is taking this path, and branch B2 is taking this path which tries to reach infinity, and the branch B3 of this complex conjugate. You can trace the path very clearly by looking into the movement of these branches B1, B2, B3, B4 subjected to the pole at S is equal to 0, pole at S is equal to -3, and the complex conjugate pair at -1 plus j as well as -1 minus j. Once after plotting the complete sketch of the root locus, we have to calculate the value of k for a given damping ratio zeta equal to 0.5. So a few more additions to be added up along with this plot. Let us recall few things related to damping ratio. While you are analyzing for a second order system, hope you could able to remember this right angle triangle in which the opposite side is omega n into square root of 1 minus zeta square, and the adjacent side is given by omega n into zeta. Therefore, tan theta will be equal to opposite side divided by adjacent side, and which will be equal to sin theta by cos theta. We have an opposite side of omega n into square root of 1 minus zeta square, and the adjacent side is omega n into zeta. Omega n and omega n will get cancelled out. Therefore, cos theta will be equal to zeta. In many of the equalities, we have used this analysis while we are doing with the second order system. Therefore, here we can take the relationship cos theta equal to zeta, and let us continue. So let me tell you the procedure to find the value of k. The first step is to draw the root locus. So we have done with the complete sketch of the root locus. Now we have to get the value of theta. With the previous equality, we know that cos theta equal to zeta, which is equal to 0.5. Therefore, theta will be equal to cos inverse of zeta. Given zeta is 0.5. Hence, theta will be equal to cos inverse of 0.5, that is nothing but 60 degrees. Once after getting the value of theta as 60 degrees, now we have to draw a line at an angle theta from the origin such that theta is measured from the negative real axis in the clockwise direction. So you have to listen carefully. We have to draw a line at an angle of theta from the origin. So we are going to draw a line from the origin at an angle of theta, which has to be measured from the negative real axis. Remember, it has to be measured from the negative real axis in the clockwise direction, and the direction should be clockwise, and it has to be measured only from the negative real axis. And the next step is to determine the intersection point of this line with the root locus sketched. So we have to find the intersection point at which this line theta at an angle of 60 degree intersect exactly on the root locus at one particular point. And we have to find out that intersection point. Once after identifying the intersection point, we have to apply the magnitude condition, and we can find the corresponding value of k. We know the procedure to apply the magnitude condition. If you are not familiar, you can go through the introduction of root locus video from the playlist control systems, and you will get a clear idea about the procedure to apply the magnitude condition and to find the value of k. Let me make use of the protractor, and let us draw a line at an angle of theta. Here in this example, we have obtained theta as 60 degree. So we have to mark 60 degree from the origin I have fixed the protractor, center of the protractor in the origin, and we have to measure the angle theta from the negative real axis in the clockwise direction. So we are supposed to measure the angle theta 60° from the negative real axis. This is the negative real axis, and we have to take clockwise direction, remember. So from the negative real axis, fixing the center of the protractor at the origin, now we have to mark the angle exactly at 60°. So 10°, 20°, 30, 40, 50, 60. This angle is exactly 60°. So let us mark the angle 60° now from the origin, and let me extend this line 60°, and this will exactly intersect on the root locus at a particular point. Let me represent it as P, and this angle theta has intersected on the root locus exactly at this point, and let me mark it as P, and now we have to determine the value of P. So let us find the point of intersection from the real as well as imaginary axis. It is very clear that this line is intersecting exactly at a point P at minus 0.45 plus 0.8. Once after identifying the point P at minus 0.45 plus j into 0.8, we have to use the magnitude condition. We know the magnitude condition is given from the characteristic equation 1 plus g of s into h of s equals to 0. Therefore, taking 1 towards the right side, g of s into h of s will be equal to minus 1. And by magnitude condition, modulus of g of s into h of s will be equal to 1. And we have to represent modulus of g of s into h of s exactly at a point P, which is given by minus 0.45 plus j into 0.8. So from the given g of s, we can substitute for g of s as k divided by s into s plus 3 into s plus 1 plus j into s plus 1 minus j, that we have to represent in the form of the roots. That is, we have two complex conjugate pole, one at minus 1 plus j and the other at minus 1 minus j. Therefore, we can write the complex conjugate pair as s plus 1 plus j as well as s plus 1 minus j, which means that if you equate it to 0, you will be getting one pole at minus 1 minus j, which is here, and the other one at minus 1 plus j, which is located here. So it has been represented in this fashion. And exactly at a point P, which is given by minus 0.45 plus j into 0.8. So now we have to replace s by this complex conjugate pole, minus 0.45 plus j into 0.8. So let us substitute for it. So the first term s has been replaced by minus 0.45 plus j into 0.8 modulus of, we have to take modulus throughout, and here let us substitute for s is equal to minus 0.45 plus j into 0.8. So minus 0.45 plus 3, you will be getting 2.55 plus j into 0.8. For the third term, similarly substitute for s as minus 0.45 plus j 0.8. So minus 0.45 plus 1, you will be getting 0.55 plus j into 1.8. Similarly, for the last term, if you substitute for s as minus 0.45 plus j into 0.8, minus 0.45 plus 1, it will be 0.55, and we have a j term here minus j plus 0.8, so we will be getting minus j 0.2. Modulus of a complex conjugate term is given by a plus jb, which will be equal to square root of a square plus b square. This is how you calculate the magnitude. Therefore, taking the denominator term towards the right side, in the numerator towards the right side, the first term, the magnitude will be given by square root of 0.45 the whole square plus 0.8 the whole square into the second term is given by square root of 2.55 the whole square plus 0.8 the whole square into, for the third term it is given by 0.55 the whole square plus 1.8 the whole square. Similarly, the last term is given by square root of 0.55 the whole square plus 0.2 the whole square, applying the formula. Therefore, k will be equal to 0.9178 into 2.6725 into 1.882 into 0.5852. Hence, k will be equal to 2.7. So, exactly at a point P, which is on the root locus, the value of k will be equal to 2.7. As the point P is on the region of root locus, we have satisfied with the angle condition. Once after satisfying the angle condition, we can find the value of k. So we have done with this problem. In the next lecture, let us solve few more problems related to the construction of root locus. Thank you.